Today's topic is about several different acid-base theories, and it's largely as a setup of saying that mostly the way you think about acids and bases is correct, but it's limiting in a way that it matters for organic chemistry. And so there's a more useful definition to at least think about when you're dealing with organic chemistry that doesn't necessarily involve donating protons. So anyway, down here at the bottom is a classic acid-base reaction, and it involves HCl and NaOH going to form water and NaCl. And so all of our definitions will need to arrive at HCl as being the thing that's an acid and NaOH as being the thing that's a base. But the acid-base definition that you probably learned first is the Arrhenius acid and Arrhenius base definitions. And basically an acid is anything that dissociates in water to give either H plus or H3O plus. In other words, if you throw an acid into water, you will end up making the pH go down as you have hydronium ion concentration go up or H plus go up. So the pH goes down because you have more H plus or H3O plus, and that's what makes an acid. The limiting thing about that definition for organic chemistry is that it has to happen in water, and a lot of organic chemistry reactions don't happen in water. Along those lines, an Arrhenius base then is something that when dissociating in water specifically gives OH minus. And so obviously if you have OH minus itself, that's a base, but anything that creates OH minus when you throw it into water is itself a base. So okay, this was the original sort of acid-base definition to work with, and then Bronsted-Lowry came along eventually later and said, well, yes, okay, but what's really causing this is that an acid is something that can donate a proton in general. And so rather than saying that this is an acid because it makes H plus or H3O plus, you just simply say it's an acid because it's giving up the H plus here, and it doesn't need to make H3O plus. It could make, say, methanol protonated or something like that. So anyway, a proton donor is a better way for an organic chemist to think about acid bases in general because we don't necessarily have water. And likewise, NaOH would be something that would accept a proton from the HCl and create water and a salt. And if we were to go ahead and think about the mechanism of this reaction, of course, you're used to seeing this drawn where you've got lone pairs on the thing that's doing the attack. So the oxygen, being the nucleophile, means that this lone pair on this nucleophile is coming over to attack the H. And so again, you can see that you are attacking the H plus part, so it's a proton donor, and the OH is getting this hydrogen from there, so it's actually accepting a proton from the HCl. And so that, again, is why we have the definitions we do. And you'll notice, of course, the pair of electrons that was a bond between the H and the Cl then becomes a lone pair on the Cl minus. And again, I would remind you that if you see Na floating around, you're better off thinking of it as Na plus and the OH as OH minus than anything else. And so at the end of this reaction, you have Na plus and Cl minus lightly associated with each other. So the key insight for Lewis was that actually this is fine and well to think of this as donating and accepting a proton, but if you think about the mechanism of the reaction, it's actually the electrons from the base that are attacking the proton, and this is what causes the entire reaction to go. So we could think of the hydrogen as the important thing, or we could instead think it's the lone pair that does the attacking that's the important thing. And so he just decided to say, okay, the right way to think about this is that the H accepts an electron pair from the nucleophile. And so an acid is anything that accepts a lone pair from a nucleophile, that accepts a lone pair from a base. And it doesn't have to be an H. And so this then allows us to expand our definition of what is an acid and what is a base. And likewise then, a base is simply something that donates an electron pair. So always it is the base that is attacking something else with its pair of electrons. So the hydroxide is a base because it's donating its electron pair to the hydrogen, which is accepting it. And so these end up saying the same things, but slightly differently. And this is limited to proton donor and acceptor, whereas Lewis acids and bases are not. So now let me give you an example of a Lewis acid, Lewis base reaction. Here we have a reaction that clearly does not fit into the typical proton donor, proton acceptor paradigm of before, but is nevertheless a Lewis acid, Lewis base sort of reaction. So a Lewis base is anything that has electron pairs to give, like say this oxygen, and a Lewis acid is basically anything with an empty orbital. And so boron with 3 fluorines on it is in fact an empty orbital because on that boron there is a spot where electrons can go. There's an empty p orbital that's left over. If you count this up, what you'll find is that the boron only has 6 electrons around it. And so you can draw a reaction that involves the lone pair from the oxygen going to fill that orbital, which creates this rather improbable looking species, but one that can in fact exist. And this is the reaction that takes place, and this is fundamentally a Lewis acid, Lewis base reaction. And this is a complex that exists. In fact, you cannot easily buy BF3 itself, but BF3 etherate is available as an item of commerce, so you can buy it without any trouble. So, acid-base reactions, you can think in terms of proton donor, proton acceptor, proton donor, proton acceptor, but you can also think of it instead as anything with a pair of electrons can be a donor of that pair of electrons. So basically, anything with a pair of electrons on it can be a base in the Lewis base sense. In other words, every nucleophile is a Lewis base. And anything with an empty orbital, or anything with a place where it can accept electrons, is a Lewis acid. Any acid is a Lewis acid, but any electrophile is also a Lewis acid. So it's just a matter, just a means of expanding the definitions of acids and bases beyond protons.